Good afternoon. Today I'll be taking your training on ADSB training program for ATSEP, basic advocate and familiarization on the ADSB system. Before we start, my name is I'll be taking you on the ADSB training for today. Before we start, housekeeping rules. If there is an emergency, please do stand up and walk in a single file. If there is a fire, the fire warden will be using the fire extinguisher at the exit. Washrooms are at the rear of the building. Once you make a left on the entrance, we can use the washroom. Before we resume with the presentation, I would like to switch your mobile phones on so we can focus on the presentation. Okay, let's start. Table of contents. Contents consists of objectives, the overview of the ADSB, system architecture, the data flow of the messages, the message structure of the TON format or TF17, coverage of the ADSB, technical parameters, compliance and workflow, this is to deal with standards, and questions, troubleshootings and questions and answers. We'll be going through two exercises, which is question 1 and troubleshooting. Moving on, our objectives after we finish this training, we'd like all the ATSEP personnel to understand ADSB system architecture and its components, identify technical parameters and message formats of the ADSB, apply IK1X10 standards and the RTC IDO 260B compliance standards, perform practical exercises and troubleshoot ADSB data. Overview of ADSB. Basically, the acronym of ADSB means long automatic dependent surveillance broadcast. Automatic, that means no pilot input is needed. Dependent, that is mainly dependent on the GNSS to operate. Without no GNSS or satellite, it cannot transmit its data or its position. Surveillance, the use of ATC for surveilling the movement of aircrafts. Broadcast means it continuously broadcasts the messages every milliseconds or microseconds. The importance in modern air traffic management of the ADSB is for monitoring the purpose of safety. Before we move on now, would you like to fly in the air on safe skies, or would you like to travel in the air without no air traffic control?
Safe skies.
Safe skies. Okay. Components of the ADSB. How the ADSB operates. You need an aircraft. You need the GNSS or the satellite to transmit, so the aircraft can establish its position according to what the satellite positions. And then after that, the aircraft needs a ground station where the receiver is located to receive ADSB data. And then finally to the users or a traffic control display, which is ASD we have at the control towers, and situation display. This is not a technical training. This is basically a familiarization of what ADSB is. Okay, ADSB system architecture. This is a generic illustration of how ADSB works. If you see 3 aircrafts in the air, it's transmitting ADSB data or ADSB report. Then you have ground stations. You have 2 masts, receiver antennas, which are ground stations. This is where the ADSB data is being received and is sent down to the ground station, processed, and then sent to the air traffic management on tower. ANSP or ADSB infrastructure, which is known as the central processing system or the CPS. We have it at tower base. So basically, position is established by triangulating the. Firstly, the aircraft is to get its position right. So it needs 3 or more satellites to triangulate its position. Once its position has been triangulated, latitude and longitude, then only all the data transmitted will be correct. So part of the messages is the speed of the aircraft type, flight number, the velocity of the aircraft, and the position of the aircraft. All those data is being sent through the ADSB data, received by the ground station, then being processed, time-stamped by the particular ground station, and is sent to the ADSB infrastructure, also known as CPS, or the Central Processing System, the main server, gets the data, converts it to asterisk data, which is being sent to air traffic management. And you see display on the ASD or A situation display of all the aircrafts that are within ADSB coverage. We'll cover on ADSB coverage in the next few slides. Now, on to ADSB data flow. This is basically just a block diagram of how ADSB data is being transmitted from the aircraft to aircraft, and aircraft to ground stations. If you can see, there are three big boxes. There are separate boxes or denotes. The first one on the far left is transmitting aircraft, which is transmitting ADSB out data. That means that particular aircraft is transmitting data out. So on the opposite right, you have receiving aircraft. So ADSB data, it does not transmit only to ground station. Other aircrafts, they need that ADSB data to know the location of aircraft within their range. If you see the cockpit, if there is an aircraft approaching, you have an alert system, which says there's an aircraft approaching. The purpose of that is what's being transmitted from the aircraft to aircraft. And the third party, which is out the ground station, is what we are basically here for. So you can see ADSB transmitter from the cockpit transmitted to the 1090 megahertz. ADSB frequency is 1090 megahertz. That means we receive on 1090 megahertz. They transmit on 1090 megahertz. So this is ADSB frequency. There's no other frequency. It's only ADSB out. That means transmitted from the aircraft is transmitted out frequency is 1090 megahertz. So our ground stations will be tuned to that frequency, our receivers. So as soon as the ADSB data comes in, you see the flow chart, the point going down to our ADSB receiver. The first block is the ADSB receiver. Once the ADSB data is being received by the ADSB receiver, remember it's being converted from RF to IP. RF and to analog and to IP. It's then converted from RF to analog, sent to the air traffic control processor. It's being time-stamped at the ground station. Once the receiver receives it, converts it from RF to analog sent down to the RPU or the computer at the ground station. It receives the data, converts it to IP, TCP IP, then it time-stamps it, what time it received it at. Time-stamps it, then it sends it to the air traffic control processor or CPS. Once it's there, it's being processed. If it's a valid data, it will process it. If it's an invalid data, it does not process it. It will not recognize that it is. Right from the ADSB receiver. If it's not a DF17, if it's not a DF17 format ADSB message, it won't receive it. It will only receive DF17 messages. It's being processed by the control processor, CPS, then it's being converted further down to asterisk data, which can work with the oral system. Then it's being sent to the CWP, or the controller working position. That's the screen you have on air traffic controllers as situation display. And then you have air traffic controller to work on the CWP. So if you can see on the receiving aircraft, that's basically the cockpit. What happens? You see that's ADSB receiver on the aircraft. It goes to the FMS of the aircraft. Collected aircraft sensors, GPS, goes to the surveillance data processor, and goes as a conflict detection. Basically, when pilots go, when they are near to, if two aircrafts are nearly colliding, that alerting system will highlight red, that there's an aircraft or something close by. That's the purpose of ADSB out. That's the purpose of ADSB data. It's not only the ground stations, it's the purpose of any aircrafts within the coverage of data being transmitted. So if any aircraft is close by, they can receive it. It will alert them there's an aircraft nearby. It will show up on the radar or their monitoring. So moving on, this is the message structure of the DF-17. Like I said, the ADSB data that is sent down from the aircraft to the receiver is called DF-17, downlink format 17. It's a type of message format that only the ADSB receivers on the ground station can only receive this kind of data. So the data is 112 bits, which is 112, bit 112. That's the whole size of the message, 112 bits. So we basically look on the data block on these ones, from the 5th bit right to the 24 bit. So the main key fields, see on the right, is the IQ address, which is the 24 bit. The position, IQ address will be the either the registration of the aircraft or the aircraft type. See, that this will be the registration of the aircraft, the IQ address. If it's coming from Nandi or Fiji, it will be Delta Quebec in the registration. Or if it's a flight number, probably that's an IQ address. The aircraft type is basically, if it's a 737, it shows 737. It's in these 8 bits, this 8-bit format. Only this data block will contain the aircraft type. 737, Airbus, so forth. Altitude, 12 bits, that's the height of the aircraft from the ground. This is called the integrity code, which are, if it's correct, it's true, it'll say tick true. If it's a false data, it'll say false. If it's a false data, it will regard it as a scramble message, invalid data. If you go to the receiver screen, if you go to this receiver subgroup, you click on it, you will see the valid data and invalid data. There is a total received signal, and you have the valid data compared to the invalid. Invalid data will be false, valid data will be true. So remember, it's all in this, in the key fields of 56 bits. Within this 56 bits is 8, 12, 2, 17, and 17. So latitude and longitude is basically the position of the aircraft. So remember, if the aircraft is moving, all these two data will be changing, latitude and longitude, as well as the velocity. Capability, this is the velocity of the aircraft. DF is basically DF-17. If it's DF-17 in this block, it will receive. If it's not DF-17, it will not receive it. Any questions? Moving on. Coverage. Coverage is basically to do with how far out an aircraft can be picked up by the ADSB receiver. If the ADSB receiver, if the aircraft is within the ADSB receiver range, like we see the circles, you see all those aircrafts are within ADSB receiver range, we can get the position of the aircrafts. If the aircrafts are too far out, within the range of the ATSB, it cannot receive it. That means that further out, the weaker the signal. If it's closer in the range, the stronger the signal, be able to receive by the ATSB receiver. You actually say, oh, it's this far, it's far out, it's the furthest. But it's actually picking up the ATSB data. It's coming closer, it will indicate that it's moving closer. So basically, the illustration is denoting coverage. How far out an ADSB. If it's a 100 nautical mile, this could be a 100 nautical mile ADSB receiver or 50 nautical mile, depending on what type of receivers you have. Moving on. Technical parameters. As technicians, we basically do preventative maintenance and corrective maintenance. Most of what we do or measure out during maintenance are this kind of technical parameters. Basically, as I stated before, frequency of ADSB data or is 1090 MHz. The refresh rate of position message is 0.5 to 1 Hz. So every time the position message is being updated with this frequency, 0.5 to 1 Hz. Position accuracy is basically typically should be less than 10 meters. It's not more than 10 meters. Should be 10 meters and less. So if the position accuracy is to do with the aircraft here, it can be within any 10 meters range. So if the aircraft is positioned there, the proximity is 10 meters. It cannot be within a particular place, it must be within that 10 meters range of position in this area. That is the standard, typically less than 10 meters. If it's 10 meters and more, it will fail. It won't be, that's a false indication. It won't say that it's a true data. So integrity levels, these are levels required by ICAO, NIC seal. This is to do with the message format. If the message comes in and meets the requirements of this particular data, which is NIC seal, I won't go into detail, and only it will pass. Which is not met as per ICAO standards, then it will say it's a false signal. Latency of received message from the ground station being sent to the air traffic controller display should be less than 2 seconds, not more. So remember, if an aircraft is coming to Honolulu, the Lakor is receiving it, before we count 1 in 2 seconds, the controller will be seeing it at Nandi or no, sorry. That's how fast it has to be. Moving on, compliance workflow. Since we work with standard safety, we are governed by ICAO, comes down to our governing body here in Fiji, which is CAP. And we are governed by the ICAO Annex 10, Volume 4. For ADSB, defines SAPs, standard and recommended practices for ADSB. Specifies message formats, broadcast frequencies, which is 1090 MHz. 978 is basically for US. Data elements, performance requirements, which is the accuracy we just went through, integrity, the refresh or update rate, and latency of message received. So, second one is ICAO ADSB implementation operations guide. This is basically, if you were to set up an ADSB system in Fiji, we need to follow this guideline, which is implementation and operations guide. Whatever is being listed here, we have to follow. Provides practical implementation guidelines for states, ANSPs, which is us, state is Fiji. We are the navigation service provider, Fiji Airports, to deploy ADSB system within ATM system. So if ADSB was new, before few years ago, more than 10 years ago, there was no ADSB. So when they brought in ADSB, they had to comply with these rules. Firstly, this is the equipment, and this is how the equipment or the project was being implemented within ATM systems. Covers planning, the planning, integration, operational procedures, which is maintenance and all, safety assessment, and performance monitoring, which is remote monitoring, RMT. We have one in tower base and one at ATM. The RTC ADO 260AB, this requires to the message format. This is to do with the airline. Every airline, they need to be following this guideline or this document. It specifies minimum operational performance standards for avionics using 1090 MHz extended speed, ADSB, and traffic information services or TS bar. DO260B is the latest revision with enhanced requirements and is equivalent to the Euro-K. That's the European standards, 102AB. This is to do with extended squidder. Before, all the old aircraft, you see the Cessnas, we had transmitting ADSB data, but surveillance data, but it was ADSC, AOC. Now we have some of those messages didn't give out the velocity of the aircraft, just showed the registration of the aircraft and aircraft type and so forth, and the velocity, I don't know, it's a velocity and the position. Now we need, like we had before, we need the aircraft type, velocity, the ICAO address, and position. So if you do not have ADSB extended splitter, which is ADSB ES extended splitter, mode S, we usually call it mode S, then you are not allowed to fly in the non-DFIR. It's mandated by CAF. So any aircraft flying within the non-DFIR has to be equipped with ADSB. If it's ADSB, extended squealer. If it's not, you'll be able to fly with it. And the purpose of the revision of the DO260B was to cater for those ADSC and ADSA and C. So those messages can be compatible with ADS mode S. That's why they had to revise. They came up with the latest version, DO260B. Now 2 questions. Questions for you. What is the ADSB broadcast frequency?
1090 megahertz.
Correct. Message type DF17, what does it represent? You recall? The message format represents position of the aircraft, IQ address, velocity of the aircraft, altitude, correct, and so forth. So basically that's what DF17 represents. Okay, moving on to troubleshooting scenario. Scenario, we have a receiver unable to receive ADSB data. So as a tech, what do? We come onto the system, we check, we confirm that all system modules are working with no errors. So we confirm all the modules are working, right? Second step we do, confirm that 0 messages received on receiver module. If there's no messages on receiver module, then you assume it's the antenna. Then the next step is testing the antenna. Test the antenna, replace it with a spare antenna. If it's coming up with the same message, then probably the receiver is working. If we replace the antenna and there is messages appearing on the receiver module, then we can say that the antenna is not working. If you replace the antenna with a new antenna, then still no message, then we assume the receiver is not working. Then we replace the receiver. If the antenna is working, then this beta transmit from aircraft is invalid. That means ADSB data is invalid. That's why I got 0 messages. If it was valid, then we have number of messages received or receiver. If receiver unit is not working, then what we do is replace. So that is a troubleshooting scenario. It's like we went on one fall on Thursday. It was the station was not booting up. It was basically a control line for a remote control. It was inhibiting the modules to power up. So we had to go and do fault solutions. Then we had observed and uncovered there was a relay that was burned. It was switching, but still there was no switching on and off. So the relays were switching, but the current was kept on going. There was no blocking. The switching on and off. So that is part of troubleshooting. Any questions?
So the it's GNSS.
Yeah, GNSS
is quasi differential GNSS. GNSS untuk sana.
GNSS dulu sana. So, if you go up to the stations, on the ground station, we even have GPS antennas. We need to position. We need to validate our position. If the GNS data or the position is invalid, then everything received on the receive antenna will be invalid. Firstly, we need to get our position correct. That's why we have a GPS antenna, and we rely to 3 or more satellites to triangulate the position. If it's less than 3, then the proximity or the accuracy will not be as to standard. Just like the aircraft, it needs to get its validated position first. Then only the data will be sent out will be true. That's why we have integrity checks, which is true or false. If it's a correct position, then only the receiver will receive it and say, oh, it's a valid position or valid data. If this data is being sent out from the aircraft and the receiver is not valid, the position is not valid, then it will not receive or process any message coming out. We have gone through faults where the GPS antenna had been faulty. Too much rain, water seeped into the antenna, short antenna. There was no position. So when we came up with the RPU, the GPS data is connected to the RPU of the computer. There was no GPS data coming from the GPS antenna, so the RPU was lost. Basically, it was lost. Any message sent by the aircraft was deemed invalid. They couldn't process it because there was no timestamp. Timestamp, you need the position to get the valid time. For example, if you have a time server is being triangulated by satellite. Time is sent from the GPS. We need 3 or more satellites to triangulate position, get the correct time or UTC time. So we need, actually it's a time, which is the time stamping of messages. Like I said, ADSB data received on the receiver, onto the RPU, timestamps. If there's no valid position coming from the GPS antenna or the GPS, there's no position, there's no correct time, what happens? It cannot timestamp. Therefore, every data coming received is invalid. It won't send anything, it will be gray. That's to do with GPS or GNSS on the ground station. So the same will apply to the aircraft as well. That's why I believe engineers, all those equipments are ready for flying out. If there's no ADSB data, if there's no, the aircraft is flying in the air, if there's no ADSB data coming out, position will be transmitted on the ATSEP frequency. They have backup procedure to follow. But then only investigations will be carried out. There was no ADSB data. Why? It's a risk. Controller will be on the screen looking at the aircraft. After a while, it's missing. You will not know where it is. Yeah, accidents in there happens in seconds. So lives are at risk. Someone will be liable, probably engineers, probably a pilot institution of ADSB transport. Any questions? Any other questions? Pinaka, I would like to thank you all for being present in the presentation. Hopefully what we've discussed and being shared has been clearly understood by the students. And Pinaka.